Now let's consider the late stages in the lives of stars. All stars eventually leave the main sequence, which is to say they eventually exhaust their hydrogen, it's all been fused into helium, and there's no more fuel available. At that point, the star has to change. With the lack of energy released from fusion reactions, the pressure on the core disappears, and so the core must begin to collapse. What happens in many stars is a two-stage process where the core collapses, but energy is released outwards and pushes off a shell of gas. The hydrogen shell will heat up and helium and fusion will begin there, so this shell will get bigger. So we have a core collapsing and attaining a higher temperature, setting off new fusion reactions, while the star will shuck off a shell of gas of low density and cooler that moves outward. In red giants, the helium core collapses until it heats to about 100 million Kelvin, and then helium fusion begins, the triple alpha process where 3 helium nuclei combine simultaneously in a collision to create a carbon nucleus. A star called a red giant is once again stable. There's a pressure balance between gravity and pressure from the helium fusion reaction, so the star is stable, but for a much shorter lifetime as a red giant. Red giants appear in this part of the HR diagram, as you can see on the left, and a cutaway view is on the right. The star now has a newly dense and hot core fusing helium into carbon, but also a large envelope of hot gas. This is the fate of the Sun, and so the red giant shell of gas, in the case of the Sun, in a 4.5 billion year period from now, will extend to the orbit of Mars, and on its way out the gas will be hot enough to essentially eradicate the biosphere. So whatever happens to life on Earth, at the end of the Sun's life, the red giant phase will likely extinguish it if we haven't made alternate plans. This is what it looks like inside a red giant. When the red giant exhausts its helium fuel, once again it's unstable, and the carbon core now must collapse. Low and intermediate mass stars, down to a few times the Sun's mass, don't have enough gravitational energy to heat up to a temperature of 600 million degrees, the temperature at which carbon can fuse and continue the fusion process. The helium and hydrogen fusion shells overcome gravity and the outer envelope of the star is gently blown away. This forms a planetary nebula. Since the Sun is in that low and intermediate mass range, this is also part of the Sun's future, the planetary nebula phase. So the star, like the Sun and those in its mass range, will die by puffing off many of its outer layers of gas, about 30% of its total mass, creating a planetary nebula. What's left behind is a white dwarf, which you can see at the center of this planetary nebula in the image. A cooling ember slowly eking its radiation into deep space and cooling forever. Planetary nebulae sit here in the Hertzsprung-Russell diagram. Let's look at a planetary nebula, the Helix Nebula, as it happens. That animation and simulation ended up with the image from the Hubble Space Telescope of the Helix Nebula. What's the state of matter involved here? Well, in degenerate matter, which is the state in a white dwarf, two particles cannot occupy the same space and the same momentum. This is a principle of quantum theory called the Pauli exclusion principle, named after Wolfgang Pauli. For very dense solids, electrons cannot be in their ground states, and so they become very energetic, approaching the speed of light. So this is a relativistic, high-density plasma, a very strange state of matter. The pressure holding up the star no longer depends on its temperature. It's as if you had a room where only one person could occupy a chair, and when all the chairs are occupied, other people have nowhere to go, and that essentially creates a kind of pressure. Degenerate matter obeys different laws of physics, in a sense counterintuitive. The more mass a star has when it's degenerate, the smaller the star becomes. And so we can see here that a white dwarf that's 1.3 times the mass of the Sun is smaller or more compressed and dense than a 1 solar mass white dwarf. The central star of the Planetary Nebula heats up as it collapses, but the star has insufficient mass to be hot enough to fuse carbon, and gravity is finally stopped by this electron degeneracy pressure, the fact that electrons do not want to have exactly the same quantum properties from one to the next. When we piece all this together, we see that stars are participating in a life cycle that extends from the formation that we talked about in dense molecular clouds, the collapse to form new stars. The stars, through their lives, lose some mass, and at the end of their lives, in the planetary nebula phase, and in particular the supernova phase, lose enormous amounts of mass. And that mass is recycled into the medium between stars to participate in a new generation of star formation. And so in that way, there is a life cycle of stars. As far as atoms and chemistry is concerned, that's important because it means that the heavy elements that are fused in the heart of a star are not held selfishly there from the rest of the universe. Many of those heavy elements are ejected into space to become part of the gas clouds that form the next generation of stars. And so over cosmic time, the proportion of heavy elements, those heavier than hydrogen and helium, has been steadily increasing through generations of star birth and death. And that's the end of this topic.